we were, so let's look at what happened last time. So last time, so we had, we saw that you can injectively immerse any compact manifold let's say of dimension k can be injectively immersed in Rn for some n. And for a compact manifold, injective immersion is nothing but being embedded, right? So I can sort of, since it's compact, I can just say sort of embedded here, sort of a stronger thing, okay? But we are after some kind of optimal capital N, right? So some optimal dimension. So we want to prove this theorem of Whitney that any manifold, be it compact or not, of dimension k can be embedded in R to the 2k plus 1. Okay, you can do better actually. So this is not optimal, but we'll only prove this. Again, and so I told you there are two ingredients, and one of them was Sard's theorem. In fact, we didn't quite need Sard's theorem. We kind of needed what I called sort of the mini Sard. So this, which is something that we saw a proof of, and the mini Sard said that, well, basically that if we proved it between Euclidean spaces. So you have, I forget what dimensions were. Maybe it's n and m. Maybe it's other way around. But anyway, what the point was that n was less than m, right? So if this is smooth, so then f of u has measure 0. So we talked about what measure 0 means in Euclidean spaces as well as manifolds, and so this was something that we saw. This is actually a corollary of Sard's theorem, which is much stronger, and one. This actually implies. So this is about open sets in Rn mapping to Rm, so Euclidean spaces, but it's easy to show that you can prove this for manifolds as well. Okay, so just because, locally a smooth map between manifolds, let me do K and L. Okay, so it's a smooth map between two manifolds, and K is less than L. Okay, so this is important. So then the image of F has measure 0 in the bigger target manifold, right, in N. All right, so this implication is an exercise. You can probably easily see this. I mean, if need be, you can cover the manifold M with countably many coordinate charts, and then in each coordinate charts you can apply the mini Sard to see that the image is 0, and then you kind of the countable union of measure 0 sets is anyway measure 0, so you would be able to say that the image in the manifold N has measure 0, right? So okay, so this is one ingredient, that if you are mapping a smooth manifold into another manifold of bigger dimension, then your image always has measure 0. Okay, so you don't have space-filling smooth curves, for instance, right? So in the you must have seen space-filling curves in topology, but those maps are not smooth, right? So anyway, so this is one ingredient. The other ingredient that we need for the Whitney embedding theorem is this notion of a tangent bundle of a manifold of M. Okay, and what is the tangent bundle? This is, of course, is any smooth manifold. Well, it's basically, as a set, it's kind of a union of all the tangent spaces. So every point on the manifold has a tangent space. It's a vector space, and you're sort of string together all these vector spaces. Sort of kind of a picture to have in mind is, yeah, something like this. Sort of here's my manifold M for every point P. Maybe I should use different colors here. Every point P, you have a sort of some kind of tangent space, a vector space attached to, associated with that point, right? And so this is just an abstract kind of sort of depiction. Okay, you don't take this literally, but that's what this tangent bundle is as a set. And now I must sort of describe what it is as a manifold, right? So anyway, so sort of you can think of it as the pair P comma X, where P is in M and X is in the tangent space at M. So this is as a set, but now I must describe the manifold structure. By the way, this tangent bundle comes with a projection map. This will be involved in the definition of the manifold structure. So there exists a projection from the tangent bundle to M that just takes this pair and just maps, forgets about the tangent vector. Okay, so somehow this is sort of goes to the point where the tangent, where the tangent space is, right? So where this tangent vector is. So this is what there's this canonical projection down to the manifold. Okay, so here's the lemma that we want. We want to say that the tangent bundle T of M is a smooth 2n manifold. So if your manifold, so if M is an n manifold, so it's a double the dimension, right? And it's a smooth manifold. So how do I? So what do we need to define a smooth? Show that it's a smooth manifold? Well, we have to give some smooth atlas, right? So here's the so we're going to use the charts on M to kind of construct it. So given a chart U comma phi for M with, let's call these with the coordinates on U would be x1 to xn. We can define an open set in the tangent bundle. Let's call it well. So this is the open set, and the tangent bundle would be the pi inverse of U. Remember that this pi is this projection, and so I guess here the understanding is that we are equipping Tm with a topology where this projection is continuous, right? So it's so these are going to be our these pi inverse of u's are going to be open sets in the tangent bundle, and we're going to define a chart from that open set to r to the 2n. Okay, so to some open set in r to the 2n. So we're going to define this mapping to let's say, let me just 2n, and how does it how does this go? Well, suppose you have some point, let's see. So you have to define what phi tilde of some point x comma v is. Well, this v is some, so in these local coordinates, remember that x belongs to u, so there's some local coordinates, and in these local coordinates, this v equals some linear combination of this coordinate vectors, right? And so you can string all of these things together to form a 2n tuple. So these are the coordinates for x, and these v1, v2 are these coordinates, these coefficients that define the vector, and this gives you a 2n tuple, right? And so this is a this is, you can show that this is a chart. I mean, this is a homeomorphism from pi inverse of u to r. Well, it's a homeomorphism to some open set, right? So it is the image is phi of u cross Rn. So these coefficients, VIs could be anything, right? So it's sort of, so if you vary these, you kind of varying in the tangent space. If you fix x1 to xn and you vary these v1s, you're varying in the tangent space. Anyway, so this is it's a homeomorphism to its image. So this is a chart. So this is an open set in R2n, and phi tilde is a homeomorphism to this image, to its image, right? So homeomorphism to this image. So it's a chart, right? So these phi tildes. So this so pi inverse of u comma phi tilde is a chart, and you can also to show that these form a smooth atlas. So the transition maps on the overlaps of charts. So if you take two such charts, let's say u comma phi and v comma psi on M that overlap, right? So such that u comma intersection v is non-empty. So then these pi inverse of u and pi inverse of v also intersect, right? And you can check that this on the intersection, these the transition map is going to be smooth. Okay, so what happens to these psi tilde and phi tilde? Well, on this overlap of these charts pi inverses, so they map to these, and the transition map, let's call it psi tilde composed with phi tilde inverse, will be mapping from phi of uv cross Rn to psi of uv cross Rn. And if you write down what this map does, so let's call it, suppose the second coordinate, the second chart V has coordinates y1 to yn, right? So this transition map will map to, well, y1 of x, y2 of x, yn of x, and then these vectors would, so you're changing the basis, right? So you kind of, there will be a, so there's a Jacobian matrix, or sort of the vectors change by the total derivative of this map. And so let me just write it down and you can sort of verify. I hope I've got these indices correct. Let's call it J2 n Vj. That is going to be the first vector, and then so this guy. So as you go along, this 1 becomes 2, 3, etc., and then the last one is yn. Okay, Vj I equal to 1 to n. Okay, and so these are the new, so the same vectors. So basically the same vector in these new coordinates y1 to yn would have coefficients which look like these. Okay, so this is sort of the change of basis. Okay, but the point is that all this whole thing is obviously a smooth map. You're just to be so this transition map is smooth. Okay, so it's certainly smooth at the level of this the manifold phi to u intersect v going to psi u intersection v, because the manifold is smooth and transition maps for charts on the manifold is smooth. But even on the part that we added, the tangent space, I mean, things vary sort of nicely. Sort of this map is basically like something like this, where it's sort of a just sort of multiplying and adding things. It's a smooth map. So the transition map is smooth. And so this defines a smooth atlas, a smooth structure on this space that we started off with, on this tangent bundle that we defined as a set earlier. Okay, so anyhow, so this is a nice manifold. In fact, so any manifold M, you can associate its tangent bundle, and so if you have so M, a smooth manifold, smooth manifold, you can associate its tangent bundle, which is a manifold of double the dimension. And this assignment is also functorial in the sense that, well, first of all, there are induced maps also. Suppose you have a map from n to n, so then you can define a derivative between at every point p, and this induces a map between the tangent bundle. So this is, what does it do? It takes p comma v to f of p comma wherever this the derivative of f at p takes v. Okay, so that's the sort of the induced map between this. This is also going to be a smooth map. So this is actually a smooth map. So between smooth map between two manifolds, you get an induced smooth map between these tangent bundles. And this is this kind of assignment of manifold to tangent bundle and smooth maps between them is functorial also. So in the sense that you have so this is this assignment is functorial, which means that first of all, if you look at the identity map between two manifolds, a manifold to itself basically induces the identity map between the tangent bundles. This is sort of something that would be obvious. And also you have something like the sort of compositions behave nicely, right? So if you have x to y to z, so these are all manifolds, and Now this is F and G. So then it induces the tangent bundle of X, tangent bundle of Y, tangent bundle of Z. So let me call it DF and DG. And these compositions behave nicely. So D of G composed with F is DG composed with DF, right? So this is sort of the second thing that you need to check when you're wanting to say that it's functorial, right? So this is like a yeah. So anyway, so this as a corollary, it follows that that if your manifolds are diffeomorphic, maybe I switch to X and Y, but you can call it M and N. So this implies that the tangent bundles are diffeomorphic. And we'll see later on, very soon, we'll see certain examples of tangent bundles, right? So, for example, the tangent bundle of the sphere S2, right? So that's actually a familiar space to us. I mean, this is something that we've seen before. So anyway, so we'll see more of that. So sort of we'll see examples of tangent bundles, specific examples of tangent bundles later. Okay. All right. So, but the thing that we'll need for the Whitney embedding theorem is that this tangent bundle is double the dimension. That's all we actually need. It's a smooth manifold of double the dimension. Okay. So, all right. So let's do this now. So let's try to get to the remaining 15 minutes. So this is something that we saw. Well, I told you. Actually, I told you incorrectly, but anyway, we corrected it now. So let me write it down. So the theorem we actually proved last time is the following, that if M is covered by finitely many coordinate charts, then there is an injective immersion. So I kind of incorrectly said embedding, but what we really proved is an injective immersion from M to Rn for some n bigger than 0, right? This is what we know. So we know that there is an injective immersion like that. Now the theorem that we'll prove now is that if a smooth manifold, let me call it, I mean, it's understood that it's a smooth manifold. So if M admits an injective immersion into Rn where n is bigger than 2k plus 1. So this m is k dimensional. Okay, this little k is the dimension of m. So if n is bigger than 2k plus 1, then you can actually improve it. Then it also admits an injective immersion into r to the n minus 1. Okay, so one lower dimension. You can go one lower dimension. Okay, so and if you keep going one lower dimension, where do you stop? Well, you have to stop at 2k plus 1, right? So the corollary of this would be that any well, the corollary is any mk. Let me now sort of add the sort of assumption compact. So compact would automatically be proper. So this would show what we want for the compact case. Okay, so any compact manifold mk can be embedded in r to the 2k plus 1. Okay, so anytime it is bigger than 2k plus 1, you can always reduce it by 1. That's what this theorem says. So this is sort of the Whitney theorem in the compact case. So this would prove Whitney embedding that we are after in the case that you have a compact manifold. Okay, so I hope that's clear, right? How this is a corollary if we prove this theorem. All right, so what's the proof of the theorem then? So this is where we use both Saad's theorem as well as the notion of a tangent bundle. So, so suppose you have this injective immersion where n is bigger than 2k plus 1. So this is an injective immersion. What we'll do is we shall project this Rn to an n minus 1 dimensional, vector subspace, right? Hyperplane, if you like. Okay, so such that if you compose with phi with this projection, it's still going to be an injective immersion. So such that okay, so let me sort of not say that at the moment. Okay, let me. Okay, so all right. Okay, so this is what we are going to do. And so first, let me sort of understand what such a subspace is determined by. So such a subspace is uniquely determined by its sort of normal direction, right? So this is something familiar to you with sort of R3, let's say, but it's normal direction. Okay, so and so if you now you're thinking of so we're going to find a suitable hyperplane, a suitable subspace of one less dimension to project Rn to. Now, what is the space of all such subspaces? Well, so to determine such a subspace, you just need a normal direction. Remember, the normal direction could be plus or minus. So it's actually, you're looking at a vector up to scaling. And so the set of such directions is the real projective space, Rpn minus 1. Okay, so you're looking basically for any point in Rpn minus 1, you get a vector in Rn up to scaling, and that determines uniquely some orthogonal, sort of hyperplane, okay, which is like a subspace of Rn. Okay, so we have this set of all such subspaces can be thought of as Rp n minus 1, this real projective space, and sort of to make it more precise, so if you take such a, as I was saying, if you take a vector or a point in Rp n minus 1, it's V is some representative, sort of line in Rn, right? So then we can define the hyperplane or this n minus 1 dimensional subspace to be all the points, all those vectors in Rn whose dot product with this V is 0. Okay, something like the orthogonal complement of V in R to the n. Okay, and this this is a hyperplane. In other words, it's this PV is, you can think of it as a, so it's actually a submanifold, right? It's something, it's Rn minus 1 canonically immersed, right, in R to the n, but sitting in some kind of slanting way, depending on what this V is, right? And so this projection we are after, now we can call it pi subscript V. So that's the projection of Rn to PV. Okay, and the key claim that will give us this theorem is that there exists some V for which, if you compose this pi with our phi, so this is still an injective immersion. Okay, and now if you um, if you if you see this, then so now you're injectively immersing into Rn minus 1, so one lower dimension. Okay, all right. Um, so this is the key claim. And in fact, we'll see that it's not just, I mean, there are plenty of such vectors or points in Rp n minus 1. So, okay, so why is this key claim true? So now sort of the proof of the key claim. So let's first understand the injectivity part of it. Okay, so let's understand. So if I choose some v and do this composition, when is it not injective? So if this composition is not injective, right? So then there exists some two distinct points such that phi p1 composed with this is the same. So which means that phi p1 and phi p2, they lie on the same line V. Remember this projection. Let me draw a cartoon of that maybe. So here's the sort of the hyperplane PV. So the projection will sort of map orthogonally sort of down to this hyperplane, right? So this Rn, everything is sitting inside Rn. Now, if 2 points, the image phi p and phi p1 and phi p2, they map to this same point under the projection, then they better be lying on the same, sort of that in that same normal direction that we are sort of projecting along, right? So if sort of the picture is something like this, so you have this normal direction given by v, right? This is sort of the projectivization of this determines the point P. So maybe I'll write it as a V here. And so this phi of P1 and phi of P2. So if it's like this, if they lie on the same line, then we are in trouble. Then it's not going to be injective. But what does it mean to lie on the same line? It means that the difference of these two vectors, P1 minus phi of P2, is the same as this direction V. Okay, in other words, V is in the image of the map. So let's define a smooth map, M cross M to, well, minus the diagonal, the product of a manifold with itself minus diagonal to Rp n minus 1, which takes a pair of distinct points. So I hope this delta M is clear. This is the sort of the diagonal submanifold, right? So consisting of pairs of points and the product that are the same. So here, if you throw it out, then P1, P2 are distinct, right? And you can map it to the difference of phi P1 minus phi P2. So this makes sense because phi is an injective map, right? So it's a phi P1 minus phi P2 will be a non-trivial, non-zero vector. Okay, so it's going to be a non-zero vector in Rn, and you're looking at its at what it defines in Rp n minus 1, projectivization of this. Okay, and so if V, so it's not going to be injective if in the image of this map alpha you have V. So if there is a pair of points P1, P2 that maps to something which equals V, so then we are in trouble. So then these lie on the same line, and then this guy is not injective. Okay, so actually I should have said that these are all sort of equivalent, right? So this is not injective if and only if there exists P1 not equal to P2 so that this lies on the same line, if and only if this happens. And so this condition of being not injective amounts to saying this V lies in the image of this map alpha. Okay, and so now we use Sard's theorem to say that there's going to, so we're going to be using this corollary of the mini Sard theorem. So So here notice that M cross M minus the diagonal is a smooth manifold of dimension 2n. Okay, because M cross M has dimension 2n, and you're throwing out a closed set, so it's some open, subset of this 2n dimensional manifold, and so it is a 2n dimensional manifold in its own right. Okay, and what is the dimension of the target? Well, the dimension of the target is n minus 1, right? That's because it's RP n minus 1. And so by our assumption, so the sort of image well, let me just say that that this 2n is less than n minus 1. All right, because by our assumption. So this is this inequality is, since we are assuming n is large by our assumption. So Sard's theorem, that mini Sard theorem corollary applies. Okay, so let me just say, so by Sard's theorem, the image of alpha has measure 0. Okay, so which means that we can pick V that is not in the image of alpha. So there are lots of things which are missed by the image of alpha. So we can pick one such V. And if you pick such a V, then, this never happens, right? So this non-injectivity can't happen. Yes, because if non-injectivity happens, it has to be in the image of this map. So this means if you pick such a V, then this guy is injective. Okay, so I've run out of time. So next time I'll use Sard's theorem again to show that you can also make sure that that you can pick a V so that it is also an immersion. Okay, and so we are going to use Sard's theorem again, and this time in the second, for this proving immersion the part, we'll use the tangent bundle. So the tangent bundle will make an appearance. Okay, so I've run out of time, unfortunately, but we'll finish off this argument the next time, and then prove the Whitney embedding theorem without the assumption of compact, right? So we are after something that holds for compact as well as non-compact. So we are going to do that as well. All right. So this is on Friday, and so we'll meet then. But right now I can take some questions if you